Hi, my name is Vlad, and I'm a researcher at INSA Lyon in France. Today, I will present to you our work, which turns around a new operating system for the requirements of edge clouds. So today, there are around 20 billion connected IoT devices, and the number is expected to double by 2027. Also, cyber-physical systems, such as process control or automotive systems, are becoming more and more autonomous, and 5G networks promise them infrastructures allowing real-time reaction to their physical surroundings. One way to provide real-time response for this large number of connected devices is to avoid the high contention in the network core and move the computation closer to the data source. This concept is named edge computing in the literature. Edge clouds are tiny data centers with generally only a couple of servers deployed as close as possible to the end users. For example, at an internet service provider or a nearby telco central office. Edge applications and their execution environments have some particular characteristics and requirements. In our work, we consider two main classes of applications: bump-in-the-wire network functions, such as 5G cellular processing or network middleboxes, and highly latency sensitive servers, such as edge caches and the control logic of IoT or cyber physical systems. In this context, edge clouds should also fulfill a number of requirements. First, they should be able to serve a relatively high number of clients. For example, a wireless cell tower can accommodate up to tens of thousands of clients. Second, given its decentralized nature, the edge computation is scattered across a large number of sites, each site having only a small number of servers due to the space and cost constraints. Third, this limited amount of resources should be shared in an isolated way between the large number of tenants. Edge clouds require two types of isolation, one between untrusted services and the second between untrusted clients. I will exemplify these two types of isolation on this figure. So here we have four groups of clients relying on different type of edge services. The first group interacts with the TLS Termination Proxy. The second group uses a machine learning inference service preceded by a firewall. The third group query a memcached server preceded by an intrusion detection system. And the traffic of the fourth group go through a longer chain of virtualized network functions. For these services, first, these services may be supplied by providers which not necessarily trust each other. Therefore, they should be isolated so that a vulnerability in one code base will not impact the others. Second, the clients also naturally do not trust each other, so they should be isolated and they should not share the same protection domain. Current edge clouds rely mainly on three abstractions in order to execute the workloads: Unix processes, containers, and virtual machines. Unix processes are one of the most lightweight execution instances used in production, but their isolation is problematic since Linux is exposed to a wide system call interface and large trusted code bases. They scale relatively well, and the startup time is much better than the two other solutions, but not enough for the churn of edge clouds. Containers are using more security features such as C groups and namespaces, but they still maintain a significant state, including signals, file descriptors, and memory mappings, which increase the attack surface. Their scalability is a bit worse than Unix processes, and their startup time is around 1 second, which is 3 orders of magnitude larger than a process. For applications requesting high performance networking, such as microsecond latencies, processes and containers can bypass the Linux kernel and DMA packets directly into user space. However, this approach can break isolation guarantees and disconnects applications from the kernel resource allocation policies. Virtualization introduces an extra hardware enforced isolation boundary, so the attack surface of virtual machines is significantly reduced. However, a hypervisor cannot generally execute more than several hundreds of virtual machines, and their startup time is in the order of seconds, so even larger than a container. So in this work, we introduced a new operating system for edge clouds, which is able to provide at the same time good isolation and scalability, microsecond startup times, and also high performance networking. So EdgeOS is based on the composite microkernel operating system, which is designed for real-time guarantees, so for real-time applications. Our new operating system is able to sustain line rate without sacrificing the isolation requirements between untrusted clients and untrusted services. EdgeOS is able to instantiate processes 170 times faster than Linux and around 5 orders of magnitude faster than containers. The number of concurrent execution contexts scale enough so that each client can have its own personal service. How is all of this possible? Mainly because of 3 ingredients. First, the featherweight processes, which are extremely minimal abstractions, wrapping only memory and a small set of simple kernel resources. Second, the memory movement accelerator, which enables strong copy-based isolation between FWPs. And a control plane optimized for high churn and dense multi-tenancy. So as I said, featherweight processes are extremely minimal abstractions, wrapping only memory and a small set of kernel resources. Each FWP is equipped with 2 message rings, one for received messages and the other for the messages to be sent. The code logic of FWP is pulling messages from the input ring processes them and pushes them in the output ring. FWPs are small enough so they can be instantiated one for every client or a reduced group of clients. EdgeOS also implements FWP checkpointing and restore in order to avoid executing the initialization process multiple times and in order to erase all context accumulated from previous clients. So basically recycle the featherweight processes used by previous clients. The second component is the memory movement accelerator. This component is in charge of all communication between untrusted FWPs. It basically copies the data from one protection domain to the other. As long as memory copying have higher bandwidth than the network line rate, this is a viable form of data movement that provides strong isolation both within and across FWP chains. EdgeOS executes this component on dedicated cores, and I will show later that even a single dedicated core can sustain throughput competitive with a middle box that relies on data sharing. This high performance is mainly due to the optimized buffer allocation outside the fast path and its strong integration with the FWP scheduler. The FWP and the MMA components described so far make up the core data plan components of EdgeOS. To handle packets coming in and out of the platform, we have ported the DPDK high performance networking library to run in EdgeOS. The control plane of EdgeOS is composed of 3 main components. the EdgeOS controller, the FWP manager, and the scheduler. The EdgeOS controller allows tenants to construct FWP chains and to specify what traffic should be routed to them. These rules are defined on the IP header and tuple and pushed to the net-in component. The FWP manager controls the life cycle of FWPs and optimize their status. It can both cache the FWPs and the connection between two FWPs so that entire chains can be restored rapidly from the cache. The scheduler determines which FWP to run on each core and activates them in response to incoming messages. So each core executes a different scheduler, a different instance of scheduler, and their coordination is via message passing to avoid shared memory synchronization. In this image, we present the main steps involving the processing of a network packet. First, when a packet is received, the net-in component performs a flow lookup and decides which FWP chain should process that packet. If there is a miss, in step 2, the FWP manager spawns a chain from its cache. In step 3 and 4, the MMA copies the packet and adds it to the input ring of the first FWP chain, of the first FWP in the chain. In step 5, the MMA messages the scheduler on the chain score to activate that FWP. This strong collaboration between the MMA and the scheduler is one of the reasons behind the high network performance of EdgeOS. In step 6, the FWP chain processes that packet, and in the end, in step 7, the last FWP in the chain asks the net out component to DMA the packet out of the network card. Now I will move to the evaluation of EdgeOS. In this figure, we present the start time of Docker containers, firecrackers, Linux processes, and EdgeOS FWPs. For Docker, we measure the duration of the Docker start command. For Firecracker, we measure the start time of the recommended hello image. For Linux, the de facto procedure to initialize a process is fork followed by exec. And for EdgeOS, we measure both the time to create a process and the time to activate a process. We can notice that EdgeOS is able to create a process 20 times faster than Linux. In the case where the FWP is known to the system and already cached, the activation time is up to 170 times faster than fork exec. Comparing with Docker containers, which are often advertised as lightweight virtualization schemes, EdgeOS performs five orders of magnitude better. In this graph, we compare EdgeOS with the OpenNet VM for two packet sizes, 64 and 124 bytes. And different length of FWP chains. OpenNet VM is a solution based on DPDK that uses active polling for communication between different cores. This solution can be considered as an ideal baseline when the number of network functions is smaller than the number of cores, which is the case in our experiment. The small packet size require an increased inter-process communication, so the CPU becomes the bottleneck as the chain increases. However, we can observe that EdgeOS is able to maintain close performance with OpenNet VM here. Moving to the large packet size, we can observe that even for a chain of 6 FWPs, the memory movement accelerator is able to sustain a throughput close to the line rate, while also providing strong isolation. So strong isolation between different FWPs. In this graph, we deployed the FWPs as middle boxes between the NetPerf client and server machines. NetPerf is a benchmark that can be used to measure the performance of different networking types. OpenNetVM and EdgeOS, OpenNetVM and EdgeOS single runs a single firewall middle box between the client and the server of NetPerf, while chain runs a chain of 2 middle boxes, a firewall and a traffic monitoring element from the click modular router. In this experiment, each customer is serviced by its own personal firewall or chain, thus preventing malicious clients interfering with the others. We can observe that for 800 concurrent clients, the latency introduced by EdgeOS is 25 times lower than OpenNetVM. Moreover, OpenNetVM is not able to host more than 800 concurrent clients, while EdgeOS can accommodate the execution of up to 2,000 firewalls on the same physical node. So EdgeOS is able to scale to more than 2 times the number of clients than OpenNetVM. In our experiments, we also considered the deployment of edge-based TLS termination proxies used to reduce the load on the main HTTPS servers by offloading the cryptographic processing to the other machines. Same as before, each client have its own personal TLS termination proxy in order to reduce the attack surface. This graph depicts the results of running an increasing number of clients making HTTPS requests. Even if both Linux and EdgeOS saturate the CPU at some point, EdgeOS is able to serve 2 times more clients, and the sustained throughput of EdgeOS is almost 700,000 requests per second, which is more than double comparing to Linux. So in conclusion, in this paper, we designed and implemented EdgeOS, which is an operating system specially adapted for the requirements of edge clouds. First, EdgeOS relies on an optimized copy-based memory movement accelerator that provides strong mutual isolation with negligible performance penalties. Second, EdgeOS is designed around minimalistic execution instances called featherweight processes, which are also optimized for high churn and dense multi-tenancy. In terms of performance, we show that FWPs can be spawned up to 170 times faster than Linux, and 5 orders of magnitude faster than Docker containers. The memory movement accelerator is able to maintain, we also seen that the memory movement accelerators is able to maintain line rate with even a chain of 5 or 6 FWPs, while in the same time providing strong isolation between different FWPs. In the case of dense multi-tenancy, EdgeOS introduces a latency which is 25 times lower than its competitor, which is OpenNetVM, and can accommodate 2 times more clients on the same physical node. Thank you for your attention, and if you have questions, please drop them in one of these mailboxes.